hour. Our next speaker is my good friend and colleague, Mohammad Akbarpour. He's going to talk about just a few seats more, the inflated value of network data for diffusion. Please.
Thank you. As you can see, Amin is a co-author on this paper, together with Suraj, who is now teaching a class on Zoom. Both of them are fantastic co-authors. I learned a lot from them. And this paper wouldn't have existed without every single one of them. It would have existed without me. So let me jump into the problem directly, which is this. So I'm going to talk about the optimal seeding problem. And the problem is pretty simple to state. You have a social network on n people, and you have some diffusion model in mind. So one example of a diffusion model is this classic independent cascade model. If I inform or infect someone, they're going to inform or infect their neighbors with some probability, and they will infect their neighbors with some probability again, and so on. And you have a budget of S seeds, and you want to inject this infection or information in the network, and your objective function is potentially to maximize the total size of diffusion. So this is a very well-known problem, and you want to choose this optimal S seeds. Now, if you have 3 seeds and I give you this network, everyone in this room is gonna tell me who are the optimal 3 seeds. If I give you a network that is a little bit more complex, it's not as easy to find who are the optimal seeds. This is a sub-network of Facebook. And in general, Kempe, Klermeg, and Tardosh, in a classic paper, which is now, I think, 5 digits cited, they show that this problem is NP-complete.
And you observe the complete network?
Yes, you observe. I'm going to go there. So that was a very good question. That the assumption here is that you observe the complete network. This is just a computational challenge. Now, this problem has a lot of applications in a lot of fields. I mean, I'm an economist. Diffusion of microfinance in economics and generally development economics is a field that has picked up this problem. You want to spread some information in these villages about some farming technology in the second paper, or some microfinance product in this first paper, or some insurance product in some other papers. There are a lot of papers recently by a group of researchers about teaching people about how to prevent HIV. And then this is a problem that started from marketing. This is a marketing problem. So from many years ago, marketing researchers have been thinking about the applications of this problem, political scientists, sociology, and so on. Now, when we have a problem that is NP-complete, but we like to solve it because it has a lot of applications, we typically go after heuristics. So there is a vast literature on heuristics for the optimal seeding problem. Now, I'm not going to go through all of these heuristics. It's going to take a lot of time. But all of them have the following big picture framework. You give me the network, I observe it. And then through some computationally feasible method, I'm going to rank all nodes of the network from 1 to n, and then I pick the top S people. Let me tell you a little bit about the findings of this big literature.
I have a question. Please go ahead. Go ahead. And the microphone is over there if you want to speak. Yeah.
So that seems sort of a little funny the way you describe it, because once I choose the top, I may know that the next 5 are useless because they're almost as good as the top, but they're sort of neighbors of it. And so wouldn't your typical greedy algorithm be slightly different from what you said? Not just
absolutely. There are papers actually even here that in this literature that do this adaptive. So when I first pick the first one, I go on pick the second one, like running a new algorithm instead of thinking of it as a static problem. It turns out that this dynamic optimization doesn't add huge value in most cases, but you can add all of those papers here too. I think even Amin and his students, or Ashan Hamid, or I forgot who was the other student, they have a paper on this, like dynamic optimization in this problem, and you can add all of them here. The key that I want to emphasize here is that all of these require network information. You could be smart and do something that's computationally feasible but not static. But you do need the network information. Now, in a way, the whole, you can summarize a lot of the papers in this literature with this quote, which is the concluding paragraph of Banerjee, Chandrasekhar, Duflo, and Jackson, which say this network targeting has important implications for policy to pick the right people to inform in order to ensure that a new idea or a product or a piece of information reaches the maximum number of people. This is the reason I picked this is that this is now this opened the literature in economics of networks. But there are other papers that do this in different settings, and all of these are empirical papers. So they do experiments and so on. And this is another paper about farming technology that has the same result. Now, what we're going to do, we're going to start from these two questions that were basically asked. In order to find these optimal seeds, you need network data. And of course, you also need computational power if you want to do actual optimum. But even for these heuristics, you need network data. And network data is both expensive, especially in this field setting. You can have the Facebook network data, but for like real world network data to inform people about something, it's pretty expensive to have precise network data. And in fact, you can almost never have a good network data in action. Like this paper by Banerjee et al., who is a pretty amazing data set. It's public and online. Anyone here who is interested can go and see the data set. 5% of nodes do not have any links in the data. And then I went and asked these people who are all, some of them are my colleagues at Stanford. I was like, what's happening? Why these people have no connections? And it turns out in the 2 or 3 times they did the survey of the network, they were not available in their home. So this is a natural limitation of data that you have. So the question is, what can you do in a world in which network data is imperfect, it's super expensive, and so on? There are a couple of papers in economics that address this problem. The first one is by the same 4 co-authors. They published in Review of Economic Studies. And what they say is that, hey, let's try to find central people without the full network data by going and asking different people in the village about their friends and friends of friends, and use local information to identify the gossips. The second paper says, let me sample 10% of the network, 20% of the network, and then use some fancy econometrics to reconstruct the whole network structure. What we're going to do here as theorists, we're going to take this approach to extreme. We're going to ask, what if you do not have any network data to begin with? And how we're going to do that? The next 5 minutes of the talk is going to tell you everything about the message of this paper. You can then leave and go and have your coffee. But what I'm going to do, anyone here can sit down a couple of hours this afternoon and do it. I'm going to take the diffusion of microfinance paper and do a simulation, redo their simulations, and then ask a different question. What I'm going to do. So before telling you what I'm going to do, let me spend 1 minute to tell you what they did. So in this paper, they went and collected the network data of 75 Indian villages by asking people about whom do you go to church with, whom do you borrow money from, whom do you get rice from, and so on. So they have this network data, which is empirical and available. And then the microfinance company went and informed a bunch of seeds, 10 to 15 people in each village. And then researchers observed who were the seeds, and then who were informed in this process about the existence of the microfinance product. And they also know who picked up the product. They know that these people were informed and they chose to participate and get a loan. So this is an amazing microdata that you have on this diffusion process in these villages. And the nice thing is that these villages are far enough that you can look at them as independent samples. Then they were like, okay, let's estimate a model of diffusion for this process. They were like, okay, people get informed. Once informed, they choose to participate or not with some probability P. It's a reduced form way to model their decision making. And then if I participate, I'm going to inform my friends with probability Cp. If I do not participate, I'm going to inform my friends with probability Cn. We are not going to impose any assumptions on whether CP is more than CN or not. I mean, we naturally expect CP to be more than CN. And then the whole diffusion stops after cap T periods. Okay, so I inform Amin informs Elon informs Bryony, and then the diffusion stops. It turns out this T is not super important and binding. So then using this amazing data of diffusion and network, they estimate these parameters. These are the parameters. They have a range. These are the midpoints of the range. The results I will show you will go through for any point in the range. So what I'm going to do now, using this, the paper shows that in the villages that nodes with eigenvectors, higher eigenvector centrality were seeded, these villages had higher total diffusion. Or in villages that nodes with a notion that they define called diffusion centrality were seeded, you observe even more diffusion. Diffusion centrality is a measure between degree centrality, how many friends you have, and eigenvector centrality, which thinks about your friends of friends and your friends of friends and so on. So what I'm going to do here is to compare diffusion centrality, which requires network data, to an algorithm that requires no network data at all, which is random seeding. The only thing we need to implement a random seeding is a list of people who live in the village. Okay, so this is probably the main figure I'm going to show you. Let me walk you through this slowly so that we know what we are doing. On the x-axis, I have the number of seeds. On the y-axis, I have the total diffusion. Let me start from here and tell you what I'm doing here. So for this blue dot over here, what we are doing is to seed the highest diffusion central node in every one of these 75 villages, inform them about microfinance, and then run this diffusion model. So that node is going to participate with probability 24%. Then they're going to inform their friends with these probabilities, and the whole diffusion stops after 7 periods. Okay, so the network is data. We are not imposing any network model, it's data. So for this one, if I do that, the total number of people who would be eventually informed about microfinance is 127. I do the same thing here. We say, hey, let's go and seed one node randomly and simulate this model on the data, and you get 60, which immediately tells you the result of the literature is absolutely right, like careful seeding is going to be highly valuable for you. Then we continue doing the same thing by 2, 3, 4, and 5 seeds, going after the top 2 diffusion central, top 2, and 2 random seeds, and so on. And if you look at this from the x-axis perspective, you will see that random with 4 seeds will do better than diffusion central seeding with 1. Okay. So this could be 3 extra seeds. This could be like times 3 seeds. This could be like e to power something seeds. That's a question that theory will help us to answer. But at least in this example, we observed that a few more seeds, in this case 3, was enough.
How big was the village?
These are villages of size around 200. So that's here on average. So this was kind of interesting and important for potentially policy, because you need no network data. You can just go after random seeds. We were like, maybe this is just expected value. Let's look at other moments. Maybe you care about variance, second moment and third moment and so on. It turns out that even if you look at the whole distribution, this is a distribution of total number of informed people, the empirical distribution for random seeding with 1 seed, which is pretty terrible relative to optimal seeding with 1 seed. Once I have random seeding with 3, this red line, red curve that you see here, it's beating the optimum with 1. So 2 extra seeds is enough for random to beat the optimum, empirically speaking, in a first order stochastic fashion. This is like a first order stochastic dominance that you see. This blue curve is an algorithm that I will tell you about. It's omniscient, it's better than the optimum. And even random with 4 extra seeds is even beating that. So we will talk about that, but I just wanted to say that it's not about expected value. Random with a few extra seeds, first order stochastic dominance. And then we were like, okay, maybe it's just about this paper. Let's go. This literature has like thousands of papers. Let's look at some other ones. For example, this is for another paper, experiment in villages in China. We use their model of diffusion, their data. These are the heuristics that they used as using network data. This is random seeding. And again, random with 5 is better than network-based seeding with 3. And it works for like every number here. So we were like, is it incidental? Is it fundamental? Like what's happening here? And then in the next 45 minutes of this talk, I'm going to convince you that this is not incidental. This is actually a fundamental property of the SIR or independent cascade diffusion model, that random with a few extra seeds is going to beat optimum. The question we're going to ask in precisely, yes.
I have a naive question. So, you are randomly seeding. How many times are you repeating this random seeding? I mean, are you talking about on average effect? Are you talking about with probability 1? What is your measure of?
Yeah, thank you. The question is, if because you then use microphone, like how did simulations? These are all like think of them as Monte Carlo simulations. We are taking averages. So this is for this one, I see the most diffusion central node of each S75 village, and I simulate like thousands of times.
So this is the average from your simulation?
This is the average. This
Okay.
one is the empirical distribution of all those simulations.
Okay, thank you. So you're talking about some kind of improvement on average, right? This could be that if you seed particularly badly, you will have a worse result than you would.
Well, this is not a worst case analysis. You're right, but this one is not the average. This one is the distribution. This is saying that even with optimum, you can have terrible outcomes. And in a first order stochastic fashion, random will do better even for any moment you look at, basically.
Okay, thank you.
Great, thank you for the question. So here is the theoretical question we're going to ask. In one world, ignore all the heuristics and computational feasibility. In one world, you have access to infinite computational power. You're going to look at the network and seed S nodes optimally. In the different world, in a second world, you're going to ignore the network structure entirely and seed S plus X nodes randomly. The question is, for what value of X that second world beats the first world? And theorem 1, X is some number between 1 and n, the number of people in the village. There is a number there, so that's an easy theorem to prove. The second theorem is that we will show conditions under which X is pretty small. So this is a way to quantify the value of both network data and computational power. I have to emphasize before going into theory and graph theory that we are not saying this is random seeding is a policy proposal. You can do better than random easily by choosing friends of a randomly chosen node, for example. This is a theoretical benchmark that helps you compare the value of collecting network data and optimizing over the network with seeding more. Okay, so it's a comparison between these two. Auction theorists of the crowd should remember Bülow and Klemperer from this comparison. They say, let's compare optimal auctions with simple auctions with one extra bidder and see which one is better. So this is a question in that spirit. And the main theorem is going to say under some conditions, random with a few extra seeds beat optimum. The theorem has a lot of clauses. So the one condition is that the diffusion should be viral. If the diffusion turns out to be very small, then random is not going to perform substantially better than, is not going to outbeat, is not going to be better than optimum. But then even optimum is going to be pretty small. And then the diffusion model is important. So there are diffusion models under which actually careful seeding and network data is highly valuable. And then I have to tell you what do I mean by a few. We will get there. Great. So I will tell you the model and then the main theorem and proof ideas. The results will go through even for power law networks, which is probably the interesting case, that even in power law networks, you don't want to go after the most central people. And then I will probably have a little bit of time to tell you about limitations of the results. If you change the diffusion model, or if you focus on the speed of diffusion as an objective function, or if you want to minimize diffusion instead of maximizing diffusion, for example, by vaccination, then network data ends up being actually more valuable than what we show. Good. So this is the one slide every network model, every network paper has. I have a social network on end nodes. I'm going to focus on undirected network for now. This is the fusion of information or flu. If you and I see each other, both of us are going to exchange this. And then you have S seeds. Okay, so you have constant number of seeds, anything more than one. So here is the diffusion model. And many people here know this model because it's called SIR, or independent cascade. At time equal to t, this node is informed. The informed node has a chance to inform his friends with probability C. Some of these are realized, some of them are not. And then this is the newly informed node. Now, I could let this guy to inform his neighbors in multiple periods. Doesn't make any difference for the results. If he can inform his friends forever, then the problem becomes kind of uninteresting, because in the long run, everyone would be informed. So I'm gonna just simplify everything and assume this guy has only one shot to inform his friends. Now, this newly informed guy at t equal 1 has a shot to inform his friends with probability C. Some of these are realized, some of them are not. These are the newly informed nodes. Again, they have a shot to inform their friends at time 2. The process continues. This is the newly informed guy, informs his friends. That one is the newly informed guy, does not inform his friend, and the diffusion stops. Okay, so that there is no cap T anymore. The diffusion stops when there is no new node who can inform their friends. So these black nodes are now my informed nodes. These now know that if the microfinance product exists. The size of this set, the number of black nodes, is going to be my objective function. Okay, so we're going to focus on that. You can change that objective function to variance or speed. We are going to focus on the expected value of this set. Okay, so let me summarize Kempe-Klemberg-Tardosh for you in one slide. We are going to use different notation, but the seeding strategy is a mapping from network. You observe the network, you know how many seeds you have, to a set of nodes. It's a set function. An example of a seeding strategy is to seed nodes with maximum degree. Another example is Christian's like a smart idea of doing it dynamically. Another idea is random seeding. These are all examples of seeding strategies. As a function of your network, how many seeds you have, and your seeding strategy, this will generate a stochastic set of eventually informed nodes. Right? The set of those black nodes that I showed you, that's a stochastic set. It's a function of realization of probability Cs. The size of this set divided by the total number of people is our objective function. Okay, so we want to maximize the expected fraction of nodes that are informed by choosing a seeding strategy, which is a pretty complicated object. It's a set function from all networks and number of seeds. So this is the optimal seeding problem. Given a network and number of seeds, you want to choose a seeding strategy to maximize this function. And this is a problem that KKT showed that this is Kempe-Klemberg-Tardosh showed that is NP complete. We don't know how to analyze this in an elegant fashion. Instead of analyzing optimum and comparing it with random, we are going to analyze a different algorithm that's better than optimum. For those of you who have not seen this omniscient idea before, this is going to be a moment of epiphany. It's actually a common technique in computer science. It's kind of simple. It says, suppose you have a planner or a designer who knows everything about all the realizations of those probability Cs. Okay, you kind of are dealing with a god who knows the future, who knows who is going to talk to whom. Now choose the optimal S seeds. You can only do better than optimal. You can always ignore that information, but you can also use it. So this is a better than optimum algorithm that turns out to be much more tractable. Okay, let me tell you what's the intellectual exercise, and then I take questions. We are going to start with random seeding. If you go to the field and collect network data, you're going to use some heuristic like eigenvector centrality or a smart heuristic, and your network is going to be imperfect. So the practical value of going to the field and collecting network data, the practical gap is the gap between these two. If I say random with one more seed is going to beat this, you know that the value of this exercise that you're going to do is one more seed. Now, I can be more generous. We can say, hey, suppose you observe the network data with no error. In fact, suppose you have computational power. You can even choose the optimum, not heuristics. And even more generous, suppose you know everything about the future. Then we're going to show that actually random with a few extra seeds is going to beat even the omniscient. Okay, so everything else is kind of in between. So the bounds we're going to show you, theoretical bounds, are so in a way too generous. Okay, so this is exactly the graph I showed you at the beginning of the talk. This is random with one seed, optimum, random with 2 extra seeds, omniscient, random with 4 extra seeds. That was a question.
Yeah, to what extent is your argument? To what extent is your argument that if I do random in a couple of time steps, I'm going to hit the people that the optimal policy would have targeted anyway?
We will almost never do that. Yeah, you will never hit the optimal policy because in a network of like in large N, if you want to seed 5 people, it's very unlikely you seed one of those.
No. What I'm saying is that in the next couple of hops of the process,
naturally
it would hit the central person.
Yeah, that's basically you're like 75% of the proof.
No, but in practical sense, my feeling is that like, my chance of like me affecting a mean versus a mean affecting me, it's not symmetric, while these models are usually symmetric.
Exactly. That's a great question. I wanted to have this conversation when we get to the limitations. So you will see the proof, or you can read it in the paper. A crucial step in the proof is that this isn't like the chance that I infect Amin is same as the chance that Amin infects me, which is a very good assumption for diffusion of, say, COVID or infectious diseases, or even some piece of fact that people share. But the chance that I can influence Lionel Messi is much less than the chance that he can send a message to me or influence me. So in a way, the way we look at these results is a joint rejection of the diffusion model that have been used to estimate these processes in practice in economics and other fields, and the diffusion model. And sorry, the importance of seeding. So either the diffusion model is different from these models that we have been using to estimate the practical diffusions, or seeding cannot be as important as we thought. So which one is true is to be decided by experiments, but it's a joint rejection. I will show you one empirical evidence that an RCT was done in practice that shows, doesn't look like seeding is as important, careful seeding. Great, so let me show you the main theorem. In order to prove any results, we need a network model. We're gonna work with inhomogeneous random graphs. Many people here know how they work, but let me explain it anyways. So each node in this model has a type, and then there is a kernel function it's a symmetric function that says for each 2 types, what is the probability that they are connected. So you have this this model, and you can have as many types as you like. In fact, you can have even uncountably many types. But here I'm going to focus on finite types. Then you can form a graph, which is a graph of K, and each element of this graph is going to be the expected number of type J friends of a type I node. This would be your graph. You can calculate the largest eigenvalue of this graph. It's going to be a useful object. So we're going to analyze the diffusion model in inhomogeneous random graphs as one relatively general network structure. So here is the main theorem. I need one more definition. So remember, this h function, little h function, was the expected value of the number of informed nodes for a given network, number of seeds, and seeding strategy. So here the expectation was taken over the realization of the diffusion process. I'm going to take another expectation over the realization of the network model, which is this inhomogeneous random graph. And then I'm going to call it the big H. So this simply says if you draw a random network from inhomogeneous random graph and you have S seeds and use the seeding strategy S, what is F? What is the fraction of nodes that are going to be informed? So here is the result. If the largest eigenvalue of this graph is more than 1 over communication probability C, then there is a function, a constant alpha, which is basically the size of the giant component of the network, that the gap between random seeding with X extra seeds and omniscient seeding exponentially vanishes.
Sorry, what was C again?
C is the communication probability, the chance that if I inform Amin, he's going to inform his friends, each one of them.
Infection rate.
The infection rate. So this is, I mean, many people here are seeing how the proof will work. This is effectively the condition under which your network has a giant component. So your R naught, if you like, is more than 1. Then you have a giant component. And in that world, the gap between these two exponentially vanishes.
So Tk is the spectral radius, right? It's dominant eigenvalue.
Pardon?
Tk is dominant eigenvalue, right?
This is the largest eigenvalue of your
graph.
So for Erdos-Shreni random graph, it's just the average degree, and you can.
Very good.
Now this is for the world in which you have viral diffusion. If you don't have viral diffusion, then this condition fails. Then random will not actually be able to compete with omniscient, but even omniscient in the like as n goes to infinity, the size of the diffusion is negligible.
Can I ask that?
Yep.
Alpha. Your alpha depends then on which parameters then?
It depends on the parameters of the network and C. Yeah.
And do you have an explicit form of alpha, or is this existential?
Well,
It's a universal constant alpha independent of X. This is a very strong indeed statement.
yes, it's independent of X. It's a function of the parameters of the inhomogeneous random graph, the kernel function and C. You know, we know like a lot about this alpha for like Erdos-Shreni random graph or a bunch of other networks. Amin is my encyclopedia, and Yagane I ask about from them. Do we know more about generally inhomogeneous random graphs alpha? I don't think so.
So to capture something, because it's a kind of probability of existence of something. So what is a kind of a heuristic intuitive level, what alpha is capturing? Probability of something, yeah.
It's the survival probability of the probability that the branching process of this network goes for infinitely many steps.
Thanks. Yeah.
Cool. So you can apply this result to Erdos-Shreni random graphs.
Question.
Go ahead.
I didn't want. I mean,
Go ahead.
I can take it later, but I feel that there is an information theoretic result you can prove here that if your graph is so boring that you could not reach in a few steps, a couple of random nodes, then there's nothing to be said. If your graph is interesting, then your optimal policy catches in a few steps random nodes. If you had seeded those nodes by symmetry, you will get to the optimal seeds anyway. Like it's without like kind of like a fundamental without characterizing anything about how the graph looks like.
Look, I mean, we haven't thought about that. It's that could work. Yeah, I would be happy to work at the top.
Now you assume your infection spread file. So when you prove your theorem, you don't have t equals 7, you have t equals infinity, right?
But that's assumption.
I think because in that node, actually in the omni whatever knowing network, there is no optimal seed. If you choose any seed in the largest component, that's optimal. And so it doesn't really matter. So there is no notion of I seed random and then 7 seeds later I reach a mean, because a mean is as good as me. We are both in this component. So that would be interesting. So you can probably prove your horizon is something like log n or so.
If t is of the order of like the diameter of the network, say the maximum distance in the network, which is typically like 5 or 6 in the networks we care about, then this probably goes through immediately. You're gonna reach everyone anyways in 5 or 6 steps. We do know that for 1 or 2 steps, even for Erdo-Shreni, you're not gonna do very well. So yeah, that would be, that's definitely something we haven't proved theorems. Great. So this you can apply to Erdo-Shreni, and the theorem just changes from, instead of eigenvector, largest eigenvector, to average degree d times the communication probability being more than 1, which is very familiar post-COVID. This is just saying that if each person on average informs one other person or more, then random seeding is gonna be fine and like beat omniscient seeding pretty quickly. And if this is less than or equal to 1, then you're not gonna do well anyways, even with omniscient. Great. So let me show you a little bit of proof ideas. I know many people here already know what is the proof, but it's a percolation idea, and I'm gonna quickly review it. So it's about communication and not friendship. What's the idea? You have a social network. A different way to look at the diffusion, instead of looking at this dynamic process, is to assume there is a God who knows who is going to talk to whom. So for each one of these two, if I'm thinking about diffusion of COVID, that if Amin and I see each other, if I have COVID, I infect him with some probability and vice versa, I can toss a coin with probability C and keep those links with probability C and kill them with probability 1 minus C. So these are the nodes that they would infect each other if one of them is infected. Okay, so I'm just looking at the future. If I inform Amin, he's going to inform his friends with probability C. Ex ante, I can say, hey, but I already know you're going to inform this guy, but not that guy. Okay, this is a static view to diffusion. So these links are irrelevant. The fact that we are friends is like irrelevant for diffusion. It's important whether you're going to actually inform me with that probability C. I can kill all of these links. And this is what we're going to call the communication network.
So I have a question there.
Yeah.
So at least if I don't think this is actually quite the right network, because if you get infected, you throw some probability of infecting me. If I get infected, I have some probability of infecting you. And so the edge from me to you and the edge from you to me in this God observed network is actually, so it's an oriented network with some edges.
Yep, perfect.
So I don't think this is actually your right network.
Yeah, Christian is always 3 slides ahead of me. So here I'm coupling the event that if I see Amin, I will inform him, and if he sees me, he will inform me. These two events happen in a coupled fashion. In general, it could be that if I see him, I will infect him, and if he sees me, he doesn't infect or inform me. That means this graph is going to be directed in that world. It will look like something like this. I'm not going to show you the proof for that, but the same result goes through here. I'm going to start with that simpler assumption of coupling these two. But then instead of dealing with giant components, you're going to deal with a strongly connected giant components who are in here. I will tell you actually a little bit how the proof will change here. Let me continue with this assumption of coupling these two events. Thank you, Christian, for asking. So this is called the communication network, and computer scientists call it percolated network. Now, why this is a fantastic network to look at? because if some node in a connected component of this network is infected or informed, I'm going to continue with informed, is informed, everyone here will be informed. I know ex ante that if this guy is informed, they're going to talk. If this guy is informed, these people are going to talk, and so on. So if I tell omniscient, hey, omniscient, you know everything about the future and you have one seed, where will you put it? Omniscient will immediately say here. If I tell omniscient you have two seeds, where will you put it? One would be here in this component, one would be here. Omniscient is super smart, it's not going to put two here. And if I say 3, it continues. So omniscient is going to be extremely smart, put one seed in every connected component of this graph. Random is going to hit each one of them with proportional probability. So if you know the distribution of the sizes of the connected components of the communication network, you're done with the proof. Because for the omniscient, you just sum up the top S components. For random, you just hit them proportionally. And that is what Erdős-Rényi and Balázs et al. And all this graph theory amazing literature has done. If the largest eigenvalue of your inhomogeneous random graph is more than 1/c, the communication probability, we know that you have you have a constant size giant component and everything else is going to be very small. If this is less than equal to 1/c, we know that this should be corrected. This was for Erdős-Rényi. We know that all components are linear size, are sublinear size. For Erdős-Rényi, we know exactly that they are log n size. For general inhomogeneous random graph, we know that they are sublinear. So all components are small relative to the size of the graph. Okay, so for Erdős-Rényi, this would be D, and that would be D, and these are all log n size. Now, how the proof proceeds? Random seeding is going to hit the giant connected components with this probability. So for any number of seeds you have, there is an extra chance you hit this, and everything else.
Sorry for being the nasty mathematician, but I think you need an extra assumption that your operator kappa is irreducible, because otherwise you could actually have two giant components.
Yeah, I should have been more. Thank you for being the nasty mathematician. It should be irreducible. The operator kappa should be irreducible. There was actually one more condition to go back to the paper. But you're absolutely right. Yeah. Yeah. Great. Thank you for correcting or clarifying this assumption that you need for this operator kappa should be irreducible. You cannot have like the two disconnected parts. It cannot be reduced, should be irreducible. So under that condition, then you're going to hit the giant component with some exponentially going to 1 probability. And small elements are irrelevant. So omniscient is going to put one seed here and a bunch of seeds in the largest of these small components. But those are so small. So what you care about is hitting the giant component. And here, omniscient is going to be very smart, pick the largest of the small components. You're going to actually potentially do terrible because there is a low chance to you hit the largest of the small components. But even if you sum these, so long as your number of seeds is constant or doesn't grow too fast, the sum of them would remain sublinear. So the fraction of nodes that are informed is still 0 in the limit. Now, of course, these are all limit results. And to see whether they make sense for real world networks, we have done already simulations and you have to look at empirics and simulation. But this tells you what's happening. Great. So, and then we have the Christian's complaint, which was right. I basically, pardon? Complaint number, yeah, 32, which is I lied to you. I mean, in a way, so I coupled these two. If you have actually the event that I inform Amin is separate from the event that he informs me, then your communication graph looks like this. I have to toss the coin. with probability C for each direction. And then we know that you will have a strongly joint connected component in the same threshold fashion. What this will change is kind of cute. If I give one seed to the omniscient is not going to put the seed here anymore. It's going to put it here. Because then I'm going to go through this path and then hit the strongly connected giant component. This is kind of too good to be true. It turns out that we can prove that the size of this path is also order log n. It's pretty small. So this doesn't make any difference. The other bound we could find in the literature was root n. If anyone knows a better bound that we haven't cited, let us know. But this is what I've learned during the course of this paper. Great. So let me show you a few extra points. How about Leo and Selena? How does this result goes through even for power law networks? The intuition is just this one example. Suppose I have this network. You have the star in the middle and everyone is connected to this star. Communication probability is 0.5. I have 1,000 people surrounding this star, this central node. Optimal seeding is going to hit the center. The total diffusion would be 500. Random seeding is going to see the leaf. Total diffusion would be 250. We bring these two here. Random with a few extra seeds. One of them is going to hit the center with exponentially high probability. In fact, with 4 extra seeds, you're already 98% of the optimal. So that's basically the question that was just asked, which is once you believe in this model of diffusion, SIR, independent cascade, SERI, all of these models that we work with, a few extra seeds are going to quickly reach to this central node anyways, either in one step or 2 steps. And then you're good to go. Putting differently, two things intuitively, 2 things can happen. Either the network has highly central nodes, in which case, because they are highly central, precisely for that, you're going to hit their friends with random seeding or their friends of friends. Or the network does not have highly central nodes, like Erdős-Saini random graph, in which case, who cares about centrality to begin with? Yes.
So now in the real world, so this is not a mathematical critique, it's sort of more a question about what happens in the real world. So in the real world, me sort of following Obama may be pretty high, the probability that Obama follows me is pretty low. If you random seed somebody in this huge Twitter network, you will get the followers of Obama. They try to influence Obama, but that is useless. And so your strategy, your random strategy would really not work. Whereas if I'm omni-knowing, I will see that all the nodes come from Obama to the people out. And so I would seed Obama and I would succeed by a factor almost n bigger. So
totally.
So that seems to indicate that for oriented networks, which sort of have something like celebrities and non-celebrities, optimum seeding is really much better than random. I mean, this is not a theorem, but it's sort of a suggestion.
Totally. So you're, yeah.
So is that one of your open problems which you are next proving?
No, the complaint number 33 is accepted. No, but totally. As I said, once you change the diffusion model, for example, to a model in which some people, actually, we do have examples. If I have time, I will show you what they are in the paper. If you have a diffusion model in which Obamas of the world are much more likely to inform their friends than vice versa, this result will fail. Yeah, if you have limited capacity of listening, like Obama is gonna listen to 100 friends only, and everyone is not gonna listen to more than 100 friends, then these celebrities, you're very unlikely to hit one of the friends of these celebrities who will inform the celebrity. Totally right, this result will fail. And that's a great next question. What we are doing here, just to repeat what I said before, So in social science, we kind of brought these epidemiology models of diffusion to understand diffusion in like human networks. And you can look at this as a critique of this exercise. This is saying, hey, this model, which is fantastic for epidemiology, SIR, independent cascade, may not be the best model for many economic interactions. We have to think about these real world considerations. Great. So you can do the same simulation for Facebook network. The same result goes through. The blue is random. I mean, let me not emphasize on this. I like this picture more. So we do simulation for all many initial number of seeds, many communication probabilities C, and we look at how many extra seeds random needs to beat eigenvector centrality seeding in Facebook network that we have. It's a network of 5,000 people, 4,000 people. And you look at all numbers, the maximum is 5. So there's no point in this space that random needs more than 5 to beat eigenvector central seeding in this network of 5,000 people, 4,000 people. Great. Yes.
What does it mean when it goes negative? It means that.
Oh, I love that question. It's actually here too. Random seeding sometimes performs better than, this is actually Christian's point. So these seeding strategies like eigenvector centrality, go after the node with highest eigenvector centrality, then the second one, then the third one. At some point, the marginal value is 0 because these are all connected to the core of the network. Random once in a while hits people here and there, and that's actually better. So once you have, like, let me show you here. Once you have more than 5 or 6 seeds, random beats a few of these algorithms just because of this. So these are actually bad strategies for large number of seeds. You want to follow Christian's idea that for the
paper from it's a
yeah. Great. So that is great. So it does become negative because random with fewer seeds is not actually out.
So my great idea algorithm. So my great idea algorithm is actually not my great idea. It's from the original paper in this literature. And we know it's within a factor 1 minus 1 over E of optimal.
Yeah.
Not with respect to omnipotence, I think, just with respect to.
Yes, totally. Yeah, greedy actually is performs in this dynamic.
This great idea stolen from the paper is called greedy. But it's better than just going down the list.
Yeah. Perfect. So let me just tell you about one empirical study that gets as close to as testing this result. So they didn't do this to test this result, but like incidentally, it's kind of close. So the same 4 co-authors have this paper in Restart, Review of Economic Studies. They do randomized control trials, and they have 2 RCTs. The first one is pure information. I'm informing people. The second one is about actually how many people did go and vaccinate. So this one, they have 6 seeds. They compare 3 seeding strategies: random seeding, going after old people, or finding the gossip of the village by local information. They ask people, whom do you think is the gossip? The next person, they form a local network and find the gossip. And then they find that random gets on average 8.1 people to be informed. These are villages of 30, 40 people. With going after gossip, this local network information, you get 11.7. And elderly is worse than both. The second experiment is they say people, hey, go and ask your friends to actually go and vaccinate. And then they do the same exercise with 6 seeds. They find that random gets 18.11 and gossip gets 23. Okay, so this is fixing the number of seeds. Gossip network seeding is basically doing better, which is completely consistent with what we claim. If you're gonna do better, but you can get it, like we can try to extrapolate and guess how many extra seeds you need in these experiments in order for random to beat. Here, random on average, each random seed is getting 3 people to adopt, 2 more people beyond the seed. So if we linearly extrapolate, you just need 2 more seeds to get to 23. even if we just cut it by saying that each random seed is going to inform just one other person instead of 2, because now we have already informed 6 people, you need 3 extra seeds to beat optimal seeding. And even if we just say that each person is going to adopt only themselves, by seeding them, you need less than 5 extra seeds. So that's kind of as close to an experiment we get. It's an RCT, so I quite like this result. Great. Let me, I have 5 minutes left. Let me not go through all of these. So diffusion model is highly important. If you generalize this independent cascade, by the way, this is one of the open questions for students of the crowd or anyone who is interested talking about it. Like, what kind of other diffusion models this goes through? That's an open question. We know that by simulation or proofs, some other diffusion models we can prove for directed communication for a specific class of networks. We can prove it. Empirically speaking, for these 2, it goes through. Evan Sadler has a paper in AER in which there is a diffusion game going on. So people make a decision, they update their belief in a Bayesian fashion. Evan was a student of Ilan. So even for his paper, this result goes through, but not for all. The classic model in which this result will not go through is the threshold model of diffusion. The threshold model of diffusion says if I inform Amin, none of his friends are going to be informed. If I inform Amin and Yagana and Ilan, and they have one friend that is common, and that friend is now going to be informed because there are 3 of his friends. This is a great model for product adoption. So that whenever you have network externality, this becomes a model. And in this case, actually, random seeding is going to do terrible. It's very unlikely for you to hit 2 friends of the same person. Or the limited capacity model that gets into Christian's empirical critique number 33, which is if Obama cannot listen to all of his 70 million followers, then this result may fail. Now let me just continue by telling you that my favorite actually example, which is this. This result will also fail for the vaccination problem if you want to minimize diffusion. So you have a network, someone attacks your network randomly and hits this guy. Now you want to defend the network by vaccination. Well, one optimal vaccination is going to pick the center and the diffusion stops. Random vaccination is going to hit the leaves, and they are kind of irrelevant in this case. In order for you to hit the center, you have to randomly hit like 75% of the nodes to finally get the center with high probability. So it's very easy to attack a network because random seeding is going to diffuse pretty quickly. Just a few seeds more is enough to defend it, at least in this example. You need many more seeds. We don't know whether this is a general result. It's kind of interesting to see whether the vaccination problem admits a similar story. So let me close by saying that there are some questions I would like empirical researchers to ask before going to the field and going after eigenvector central or like diffusion central nodes. The first one is like, what is the underlying diffusion process? This is a question that's important to ask before doing any kind of diffusion experiment. Do you hope the diffusion to go viral? If you hope to go, for example, think of an election. So if you have to get more than 50% of people to believe in you, and anything less than that gives you a utility of 0, then you do want a viral diffusion of something. Then in that case, the story is different than a case in which your utility is just an increasing function of the number of people who are informed. There is no step function. This is an important case for, say, vaccination. If you need 80% of the people to believe vaccination is good to get into herd immunity. It's like that's an example of this situation. Do you care about the speed? If you care about the speed, then it's important to go for central people. And do you want to maximize or minimize diffusion? One last comment I have is that there is a statistic that measures the economic value of network seeding. The statistical value is always significant in these experiments and papers we have seen. Like seeding central people is always statistically better than randomly seeding. But there is a way to measure the economic value, which is tell me how many extra seeds I need for a network agnostic strategy like random seeding to get to say 95% or 99% of this network guided seeding. This is telling you something about the fact that like I know how much each seed costs, and if you tell me 2 more seeds are enough, then I know the value of my exercise beyond the statistical significance. We did this for a bunch of papers. There is a Python package you can use to do it for any other paper. So for these like 2 papers, for example, you need something between 1 to 3 extra seeds to get to 95% of the heuristic that these papers suggest. It's a good heuristic. So I find this to be a good way, at least for empirical researchers, to think about it. And I'm going to close by this picture. So one nice thing about being in a business school is that when you write a paper, they interview you and your co-authors, they write a piece about it, and then they ask an artist to read the piece and depict something and draw something. So this is an artist reading our interview and turning it into an art. So it is
I have a question and possibly a comment depending on the answer of your on the question. So you said this, you had an undirected link, and then you said in reality it should be 2 directed, one going from A to B and the other. Did you mean that these things should be independent and have the same distribution?
So yeah, what we are saying here is that if I inform Amin, he's going to inform me with probability C. If you inform me, I'm going to inform Amin with probability C, and these 2 are independent. So what we need here is that these 2 are symmetric. In that case, even these 2 can have different probabilities than these 2, but we need symmetry in here.
So then my comment is that if you have one edge going, you decide to flip a coin, should there be an edge from A to B, and then you flip another coin, should there be an edge from B to A? And I claim that it's enough to have one edge, because rather than having A to B or B to A, you could say, I will use the first coin flip for the first time. I might inform someone, could be the direction, and then the second toss will be the second time you will use it. But then you realize that you will never use it more than in one direction. So it's enough to flip one coin. So I think you can actually consider the undirected network only. This is sort of an old epidemic result. If the things are independent, you don't need to consider the direction. You interpret the undirected edge as if A gets infected, he or she will spread it to B. Or if B gets infected, he or she will spread it to A, because you will never be considering going in both directions.
Yeah, but I'm worried about this guy. So if I inform this guy will not be informed.
Oh, sorry, your initial network is a directed network. Is that?
No, the initial network is an undirected network. The communication has direction. So if I inform this guy over here, I know ex ante that this guy is not going to inform this guy back. But this guy is going to inform this guy. So I'm not sure if it works.
Well, maybe not. I think probabilistically it's enough to have one edge, but I might be wrong.
It's a nice trick, but here the seeding appears. The seeding is decided after the appearance of the network. So you can't pull that trick. It's a very nice trick, but it's not applicable.
Any more questions, concerns? Are we going to have lunch?
Yes, that's great for
Perfect, thank you.
Thanks.